Picture a face lit by flickering firelight somewhere in Europe, maybe 10,000 years ago. The flames dance in the darkness, and when the light catches just right, you see them. Blue eyes. Bright, clear, startling blue, staring back at you from across thousands of years of history. Here's what makes that image so incredible. Go back just a few thousand years earlier, and those eyes didn't exist anywhere on the planet. Not in Africa, not in Asia, not in Europe. Nowhere. Every single human being on Earth had brown eyes. Then suddenly, impossibly, blue eyes appeared. And here's the really mind-bending part. Scientists have traced the genetics, run the DNA analysis, checked and rechecked their work. The conclusion? Every blue-eyed person alive today, all 600 to 800 million of them, carries the exact same genetic mutation. Not similar mutations, the exact same one. Which means somewhere, sometime between 6,000 and 10,000 years ago, one person was born with a genetic typo in their DNA. And that mistake, that random copying error in a single gene, spread across an entire continent. Think about what that means. If you have blue eyes, you can trace your ancestry back to one individual, one moment, one mutation. You're part of the largest extended family tree in human history, all branching from a single ancestor who lived somewhere near the Black Sea thousands of years ago. But here's where it gets really strange. Blue eyes shouldn't have spread at all. From an evolutionary standpoint, they're basically useless. They don't help you see better. In fact, they might actually make you more sensitive to bright light. They don't protect you from anything. They don't make you stronger or faster or smarter. They're just there, a random variation that serves no obvious biological purpose. Yet somehow this meaningless mutation spread through ancient Europe like wildfire. Today, up to 80% of people in some Scandinavian countries have blue eyes. In Finland, Iceland, Estonia, the numbers are staggering. But step outside of Europe, and blue eyes become increasingly rare. In Asia, almost non-existent. In Africa, virtually zero outside of populations with European ancestry. So what happened? How did a completely random, functionally neutral mutation become one of the most recognizable traits of an entire continent? Scientists have been arguing about this for decades, and the theories range from fascinating to controversial to downright uncomfortable. Some researchers believe it's pure genetic drift, just random chance amplified by small founding populations. Others think sexual selection was involved. The ancient Europeans found blue eyes attractive and preferentially chose blue-eyed partners. Then there are the more controversial theories involving vitamin D synthesis, light absorption in northern climates, and adaptations to dramatically different environments as humans migrated out of Africa and into the frozen north. The truth is, nobody knows for certain, and that uncertainty is what makes this story so compelling. We can trace the mutation to a specific gene, OCA2, which controls melanin production in the iris. We can date approximately when it appeared. We can track how it spread across Europe during the Neolithic period. But we can't definitively say why it succeeded when thousands of other random mutations disappeared without a trace. What we do know is this. The person who first carried this mutation lived during one of the most transformative periods in human history. The ice sheets were retreating. Agriculture was beginning to replace hunting and gathering. Populations were exploding and migrating in waves across continents. Everything about human society was changing, and somehow, in the middle of all that chaos, blue eyes appeared and thrived. This is a story that spans ice ages and migrations, survival and adaptation, pure chance and possibly something more. It's about how a tiny genetic accident became woven into the identity of hundreds of millions of people. How a mutation that shouldn't matter somehow came to define entire populations. how one person's DNA echoes through millennia to touch the faces of people living today in Stockholm and Dublin and Berlin. And maybe most fascinating of all, it's a story that's still unfolding. Because blue eyes might be slowly disappearing, or they might not. The genetics are more complicated than we thought, the future more uncertain than we assumed. So if you're settling in for sleep, you're in the right place. Because we're about to travel back through thousands of years to understand how those eyes that shouldn't exist came to be staring back at us from millions of faces across the modern world. The journey starts in a world where everyone's eyes were brown, and nobody could have imagined what was coming. For hundreds of thousands of years, every human who ever lived looked into the eyes of another human and saw the same colour staring back. Brown, deep brown, light brown, amber, hazel variations on a theme, but always fundamentally brown, always melanin-rich, always dark. This wasn't an accident. This wasn't just one option among many. Brown eyes were the only option, the universal human baseline, coded into our DNA as firmly as having 2 legs or 10 fingers. Your ancestors 200,000 years ago had brown eyes. Their ancestors 1,000,000 years before that had brown eyes. Go back 5 million years to the earliest hominids walking upright across the African savannah, and you'd find brown eyes staring out from faces that barely resembled our own. The science behind this is straightforward, almost brutally simple. Eyes need melanin. Specifically, the iris, that coloured ring around your pupil, contains melanocytes, specialised cells that produce melanin pigment. The more melanin you have in your iris, the darker your eyes appear. Brown eyes have high concentrations of melanin in the front layer of the iris. This isn't just about appearance. That melanin is doing something critical. It's protecting the delicate structures inside your eye from ultraviolet radiation. Think about where humans evolved. Africa, specifically equatorial and sub-Saharan Africa, where the sun beats down with an intensity that people from northern latitudes can barely comprehend. UV radiation levels that can cause cellular damage, cataracts, macular degeneration. Under those conditions, melanin in the iris isn't cosmetic. It's survival equipment. It's the difference between maintaining good vision into your 40s and 50s, when you might have grandchildren to help raise, versus going blind in your 30s, becoming a burden on your group when resources were always scarce. Natural selection doesn't mess around with survival equipment. Any mutation that reduced melanin production in the iris would have been ruthlessly eliminated from the gene pool. Individuals born with lighter eyes would have suffered higher rates of eye damage, reduced hunting and gathering effectiveness, lower reproductive success. Their genes wouldn't spread. They'd disappear within a generation or two. So brown eyes persisted, not because they were somehow better in any abstract sense, but because in the environment where humans evolved, they were necessary. They were the baseline, the standard model, the only design that made sense. Now, take a moment and think about where you're watching this from. What time is it right now? Are you lying in bed as the sun comes up, sitting in a darkened room at 2 a.m., listening while you commute through a city at dusk? Drop a comment and let me know. Because the fact that humans now live everywhere, across every latitude, in every climate and light condition imaginable, that's actually the beginning of our story. We started in one place, under one sun, with one eye colour. What happened next changed everything. Our brown-eyed ancestors began their expansion out of Africa in waves. The first major migration happened maybe 1.8 million years ago, when Homo erectus walked into Asia and Europe. They carried brown eyes with them, every single individual. Then came the Neanderthals, spreading into Europe around 400,000 years ago. Brown eyes. There's Denisovans moving across Asia. Brown eyes. And finally, around 70,000 to 60,000 years ago, modern humans, Homo sapiens, began leaving Africa in the migration that would eventually populate the entire planet. They walked into the Middle East. Brown eyes. They moved into India and Southeast Asia. Brown eyes. They crossed into Europe. Brown eyes. They reached Australia, then Siberia, then crossed the Bering Land Bridge into the Americas. Every step of this incredible journey, every new territory claimed, every adaptation to new climates and new resources was accomplished by people who all had the same dark eyes. For the humans making these journeys, the concept of any other eye colour simply didn't exist. It wasn't part of their reality. Imagine trying to explain blue eyes to someone who had never seen them, who had no reference point, who lived in a world where every human, every ancestor, every person in every story told around every fire had brown eyes. It would be like describing a new primary colour, something that doesn't fit into the existing spectrum of human experience. The genetic instructions for brown eyes were so deeply embedded in the human genome that they might as well have been permanent. They were part of the package deal of being human. You got 2 legs, 2 arms, a big brain and brown eyes. That's just how humans were built. But here's what those ancient brown-eyed migrants didn't know, couldn't have predicted, wouldn't have believed if you'd told them. Some of them were walking into environments where the rules were about to change, where the survival calculations that had held true for millions of years were about to be turned upside down. As humans pushed further north into Europe and Asia, they were entering territories unlike anything their species had encountered before, lands where winter could last 8 months, where the sun hung low on the horizon even at midday, where darkness dominated and the intense UV radiation of the African savanna was replaced by dim, filtered light scattered by clouds and absorbed by forests. In these new environments, the protective melanin that had been so valuable in Africa was becoming less critical. The UV threat was diminishing, but that alone wouldn't have been enough to change anything. Evolution doesn't remove traits just because they're no longer necessary. Brown eyes would have persisted indefinitely simply because there was no selective pressure against them. What was needed was a mutation, a random copying error in the DNA of some child born thousands of years after humans had settled in the north, a mistake that would normally disappear without a trace, but that in this new environment, under these specific conditions, might somehow provide an advantage, might give its carriers some reason to survive and reproduce more successfully than their brown-eyed neighbours. The stage was set. Humans had spread across the northern territories, carrying their brown-eyed genes into lands of darkness and ice. Populations had become established, had learned to survive the brutal winters, had adapted culturally and physically to their new homes. They were hunting mammoths across the frozen plains of Europe. They were building shelters from snow and ice. They were developing technologies that would have amazed their African ancestors. But they all still had brown eyes, every single one. The genetic instructions remained unchanged, passed down through thousands of generations without deviation, until one day, probably around 10,000 years ago, probably somewhere near the Black Sea region, probably in a moment that seemed completely ordinary at the time, a child was born who would change the human story forever. This child carried a mutation, a single letter change in the genetic code, a mistake in the DNA copying process that affected melanin production in the iris. And when people looked into this child's eyes, for the first time in human history, they didn't see brown staring back. They saw something impossible, something that had never existed before in millions of years of human evolution. They saw blue. Around 45,000 years ago, a small group of humans stood at the edge of everything they had ever known. Behind them lay the warmth of the Middle East, the familiar territories their ancestors had occupied for tens of thousands of years. Ahead lay Europe, a land of ice and shadow that would have seemed like the edge of the world itself. They went anyway. We don't know exactly what drove them. Maybe population pressure pushed them north. Maybe they were following migrating herds of mammoth and reindeer. Maybe they were just curious, driven by that restless human impulse to see what lies beyond the horizon. Whatever the reason, they crossed into a world unlike anything their species had experienced before. Ice Age Europe wasn't just cold. It was a landscape that seemed designed to kill anything foolish enough to try living there. Winters lasted 8, 9, sometimes 10 months. Summers were brief, unreliable, barely warm enough to melt the surface ice before the cold returned. The sun, when it appeared at all, traced a low arc across the southern sky, providing weak, slanting light that did little to warm the frozen earth. These weren't the humans who had survived the bottleneck 800,000 years earlier. Those had been African populations adapted to heat and savanna. These were their descendants, already changed by millennia of evolution, but still fundamentally tropical animals trying to survive in a world of permanent winter. The landscape they entered would have been alien beyond imagination. Endless plains of frozen tundra stretched from the Atlantic coast to the Ural Mountains. Glaciers thousands of feet thick covered Scandinavia, the Alps and much of northern Europe. The sea level was 400 feet lower than today because so much water was locked up in ice, exposing vast continental shelves that are now deep underwater. But it wasn't empty. The cold had created its own ecosystem, strange and magnificent. Woolly mammoths moved in enormous herds across the frozen grasslands. Cave lions, twice the size of their modern African cousins, hunted in the twilight. Giant elk with antlers 12 feet across browsed on what vegetation they could find. Woolly rhinoceros, cave bears, hyenas adapted to the cold, all competing for survival in this frozen world. And now humans were competing too. The first arrivals must have struggled terribly. Everything they knew about survival had to be relearned for these conditions. Fire became more than a convenience, it became the difference between life and death. Every night was a battle to keep flames alive, to gather enough fuel to last until dawn. Caves weren't just shelter, they were survival refuges, places where body heat could accumulate, where a fire could be maintained against the endless wind. Food was a constant crisis. In Africa, you could gather fruits, roots, plants year-round. Here, winters meant no plants at all. Everything had to come from hunting, from tracking and killing animals that were themselves desperate to survive. Miss too many hunts, and your group starved. It was that simple, that brutal. The archaeological record from this period shows just how desperate things sometimes got. Butchered bones reveal that early Europeans used every part of every animal they killed. Bone marrow was extracted from even the smallest bones. Brains were consumed for their fat content. Hides were scraped and processed with an intensity that suggests they couldn't afford to waste a single scrap. These weren't people living comfortably. These were people on the edge, surviving one day at a time. But they were also adapting. Generation by generation, natural selection was working on them, changing them in ways both subtle and profound. The changes weren't random. They were responses to specific environmental pressures, evolutionary solutions to the unique problems posed by life in permanent winter. The first major adaptation was in their skin. Human skin color is controlled by melanin, the pigment that protects against ultraviolet radiation from the sun. In Africa, where sunlight is intense year-round, dark skin is a massive evolutionary advantage. It prevents UV damage, protects against skin cancer, preserves folate, a vitamin crucial for fetal development. But in Ice Age Europe, that protective pigmentation became a liability. Here's why. Human bodies need vitamin D to function. It's essential for bone growth, immune function, calcium absorption. We can get some vitamin D from food, but humans primarily produce it in our skin when exposed to ultraviolet light from the sun. In Africa, this isn't a problem. There's plenty of sunlight, and even heavily pigmented skin can produce sufficient vitamin D. But in northern Europe, with its weak winter sun, long nights, and months when the sun barely rises above the horizon, dark-skinned people would have struggled to produce enough vitamin D. Children would develop rickets, a bone disease that causes deformities and makes survival difficult. Adults would experience weakened immunity, making them more susceptible to infections in an environment where any illness could be fatal. Natural selection responded exactly as you'd expect. Individuals with lighter skin could produce more vitamin D from the limited available sunlight. They had healthier children, stronger bones, better immune function. Over thousands of years, the European population shifted lighter and lighter, trading UV protection they no longer needed for vitamin D production they desperately required. But skin color wasn't the only thing changing. Body proportions were shifting too. The new Europeans were developing shorter, stockier builds compared to their African ancestors. This wasn't random. It was thermodynamics. Compact bodies with shorter limbs lose heat more slowly, a crucial advantage when every calorie matters and cold is your constant enemy. Nasal passages were changing as well, becoming narrower and more prominent. This adaptation helped warm and humidify the brutally cold, dry air before it reached the lungs, preventing tissue damage and reducing water loss through breathing. Archaeological analysis of early European skulls shows these changes happening in real time, evolution visible in the fossil record. Most remarkably, brain size was actually increasing, not because Ice Age Europeans were necessarily smarter than their African cousins, but because survival in the north required different cognitive skills. You had to plan ahead more carefully, prepare for months of scarcity, remember complex information about animal migrations and seasonal patterns. You had to develop technologies that your ancestors never needed. Sophisticated clothing, elaborate shelters, food storage techniques. Natural selection favored individuals who could master these challenges, who could learn quickly and innovate when old solutions stopped working. Over millennia, this pressure refined human intelligence in ways that would prove crucial for our species' future success. But the physical changes weren't the whole story. These early Europeans were also developing unique cultural adaptations, survival strategies that were learned rather than inherited. They were creating some of the most sophisticated stone tools ever made, delicate blades and points that required enormous skill to manufacture. They were developing composite tools, combining stone, wood, bone, and sinew into weapons and implements of remarkable complexity. They were making clothing, real clothing, not just animal hides draped over shoulders, but carefully tailored garments with stitching and multiple layers. Archaeological sites preserve bone needles from this period, evidence of sewing technology that allowed humans to create weatherproof outfits that could keep them alive in temperatures that would kill an unprotected person in hours, and they were creating art. The cave paintings of Ice Age Europe, horses and bison and mammoths rendered in ochre and charcoal on cave walls. These weren't just decorations. They were evidence of human minds capable of symbolic thought, of representing reality in abstract form, of communicating complex ideas across generations. In the flickering light of cave fires, surrounded by the grinding cold of endless winter, humans were discovering they could create beauty even in the hardest places. Small bands of these adapted, resourceful, increasingly sophisticated humans spread across Ice Age Europe. They weren't numerous, probably never more than a few tens of thousands at any given time, spread across the entire continent. But they were surviving, holding on, maintaining human presence in a land that seemed determined to reject them. They lived in caves and rock shelters, anywhere they could find protection from the wind. They followed the herds, tracking mammoth migrations across the frozen plains, hunting reindeer in the brief summers when the herds moved north. They developed territories, ranges that different groups returned to year after year, learning every detail of the landscape, every place where game might be found, every source of tool-making stone. And in these small scattered bands, huddled around fires in the endless dark, children were being born. Generation after generation, each carrying the genetic adaptations that allowed survival in this brutal world. Lighter skin, stockier builds, enhanced nasal passages, brains wired for the complex problem-solving that kept their parents alive. Somewhere in this frozen darkness, in a cave whose location we'll never know, in a band of humans whose names are lost to time, something else was about to happen. A child was about to be born carrying a mutation that had never existed before. A tiny change in a single gene that would alter nothing about survival, provide no obvious advantage, solve no pressing problem. A mutation that would create the first blue eyes humanity had ever seen. But nobody watching that birth could have known they were witnessing the beginning of a genetic revolution that would sweep across Europe and persist for the next 45,000 years. They just saw another child, another mouth to feed, another chance for their desperate gamble in the frozen north to continue one more generation. The darkness of Ice Age Europe held many secrets. This was about to become one of its strangest. Somewhere between 6,000 and 10,000 years ago, in a region near the Black Sea, something impossible happened. A child was born with eyes the colour of the sky, not brown, not dark, not any shade that had ever appeared in human eyes during our entire evolutionary history. Blue, clear, bright, startling blue. The parents must have been terrified, or amazed, or both. Imagine it. You're a hunter-gatherer living in what's now Ukraine or Romania. Your whole world is made up of maybe 150 people, all with brown eyes. Every human you've ever seen, every ancestor you've heard stories about, every face in your memory, brown eyes. Then your child is born and their eyes are the colour of deep water, the colour of summer sky, a colour that doesn't exist in human eyes. What would you think? That the gods had touched your baby, that something had gone wrong, that your child was special, cursed, blessed or broken? We'll never know what they thought, but we know what happened, because that child survived, grew up, and had children of their own. And those children carried the mutation forward into the next generation and the next, spreading it across continents over thousands of years until today, when hundreds of millions of people walk around with those same impossible blue eyes. Every single one of them descended from that one child, that one moment, that one tiny genetic accident that changed nothing important about being human, but somehow changed everything about how we see each other. This isn't speculation. This isn't ancient legend or educated guessing. This is hard genetic science, discovered through some of the most remarkable detective work in modern biology. In 2008, researchers at the University of Copenhagen, led by Professor Hans Eiberg, published findings that would rewrite our understanding of human eye colour variation. They had been studying families with blue eyes, looking at genetic markers, tracing inheritance patterns, trying to understand how this trait moved through populations. What they found was stunning in its simplicity. All blue-eyed people, regardless of where they live today, whether they're Swedish or Australian, Russian or American, Irish or Argentinian, they all share an identical genetic signature in a specific location on chromosome 15, the exact same mutation, not similar, not parallel, identical. This could only mean one thing. Every blue-eyed person on Earth inherited this trait from a single common ancestor. One person, living somewhere near the Black Sea, between 6,000 and 10,000 years ago, the mutation occurred in a gene called OCA2. Now, this gene had been well studied because mutations that completely disable it cause a condition called oculocutaneous albinism, which results in a complete lack of pigmentation in the skin, hair and eyes. But the mutation that created blue eyes didn't disable the gene. It did something far more subtle and far more interesting. Just next to the OCA 2 gene sits another stretch of DNA called HERC2. This region acts like a genetic switch, controlling how much the OCA2 gene gets expressed, how much melanin production happens in the iris of the eye. The blue eye mutation didn't damage the melanin production system. It just turned down the dial on the switch. Think of it like a dimmer on a light fixture. The bulb still works perfectly. The wiring is fine. But someone installed a dimmer switch that reduces the brightness to about 20% of what it used to be. That's essentially what happened in the eyes of that first blue-eyed child. The iris, the coloured part of the eye, gets its colour from melanin, the same pigment that colours our skin and hair. More melanin means darker eyes. Brown, hazel, dark amber. Less melanin means lighter eyes. But here's the fascinating part. Blue eyes don't actually contain any blue pigment. None. 0 blue molecules anywhere in a blue iris. Blue eyes are blue for the same reason the sky is blue. It's a trick of light scattering. The iris contains very little melanin, and the collagen fibers in the stroma of the iris scatter shorter wavelengths of light, blue light, back to the observer while longer wavelengths pass through. It's called Rayleigh scattering, and it's the same physics that makes the sky look blue on a clear day. So blue eyes aren't coloured blue, they're coloured nothing, and the nothing looks blue because of how light behaves. The first blue-eyed child wasn't born with something new. They were born with something missing. Less melanin in their irises than any human who had come before them. A reduction, a dimming, a loss that somehow became beautiful. But here's the real mystery. The question that should keep you awake at night. Probably won't, because this is sleep content, but should. Why did this mutation survive at all? Most mutations don't. The vast majority of genetic changes are either neutral, having no effect whatsoever, or harmful, reducing the survival or reproductive success of the individuals who carry them. Natural selection eliminates harmful mutations quickly, sometimes within a few generations, and from a survival perspective, blue eyes should have been eliminated. They offer no obvious advantages. In fact, they come with measurable disadvantages. Blue eyes are more sensitive to bright sunlight than brown eyes because they contain less melanin, which means less natural UV protection. People with blue eyes are more likely to develop certain eye conditions, more likely to experience light sensitivity, more prone to sun damage. In the environment where this mutation first appeared, somewhere near the Black Sea where sunlight could be intense, especially reflecting off snow and water, blue eyes should have been a handicap. Parents with blue-eyed children should have had slightly lower reproductive success, because those children would have had slightly worse vision in bright conditions, slightly higher rates of eye problems, slightly reduced ability to hunt or gather effectively. And yet the mutation spread. Not just survived, but thrived, expanding from one child to become one of the most distinctive features of European populations. Within just a few thousand years, blue eyes had spread across vast territories, becoming common in northern and eastern Europe, reaching frequencies of 80% or higher in some populations. Something was happening, something that overcame the disadvantages and made blue eyes not just survivable, but somehow advantageous. Or at least acceptable enough that natural selection didn't eliminate them. We'll explore the theory about why in a moment, the possible explanations for this seemingly impossible spread. But first, sit with the strangeness of the discovery itself. The genetic research that revealed this single origin point required examining DNA from people across the globe, blue-eyed Danes and blue-eyed Turks, blue-eyed Australians descended from British colonizers, and blue-eyed Russians from Siberia, blue-eyed Americans whose ancestors came from a dozen different European countries. Every single sample showed the same mutation, not similar, identical. The same genetic markers flanking the mutation, the same pattern of linkage disequilibrium, which is the fancy genetic term for chunks of DNA that travel together through generations, because they're physically close on the chromosome. This told the researchers something remarkable. The mutation was recent enough that there hadn't been time for the surrounding genetic markers to get shuffled around by recombination. In genetic terms, 6,000 to 10,000 years is basically yesterday. Not enough time for the mutation to arise independently in different populations. Not enough time for the surrounding DNA to change significantly. This was a single event. One moment, one child, one ancestor. And suddenly, the diversity of human eye colour we see today, all the blues and greens and hazels that had never existed before, they all trace back to that moment near the Black Sea, to a baby whose eyes didn't have enough melanin, to parents who looked at their strange-eyed child and, for whatever reason, didn't abandon them or mark them as cursed, but raised them, protected them, let them grow up and have children of their own. We don't know what that first family thought. We don't know if blue eyes were seen as beautiful or disturbing or spiritually significant. We don't know if that first child was celebrated or feared or simply accepted as different. But we know they survived. We know the mutation persisted. And we know that within a few thousand years those blue eyes had spread across Europe like wildfire, changing forever how humans looked at each other, how we recognized kin and strangers, how we defined beauty and otherness, all from one child, one moment, one tiny change in one gene that reduced melanin production, just enough to turn brown eyes into something the world had never seen before. That child's descendants now number in the hundreds of millions. Their eyes look out from every continent. Their genetic legacy has become one of the most visible markers of human diversity. A trait that divides populations, marks ancestry, influences how we see beauty and identity. And it all started with a mistake, a mutation that shouldn't have mattered. A small reduction in pigmentation that should have been lost to history but wasn't. The question is, why? What happened next that turned this genetic accident into one of the defining features of European populations? What forces, natural or cultural, spread blue eyes across a continent in what amounts to a genetic instant? The answers, as we're about to discover, are stranger than the mutation itself. So here's the puzzle that keeps geneticists up at night. Blue eyes offer no survival advantage. None. They don't help you see better. In fact, they make you slightly more sensitive to bright light. They don't protect you from UV radiation. Actually, they make you more vulnerable to certain types of eye damage. They don't indicate superior health or genetic fitness. They're just different. A quirk of pigmentation that happened to one person 10,000 years ago somewhere near the Black Sea. And yet, within a few thousand years, blue eyes had spread across Europe like wildfire. By 4,000 years ago, some populations in northern Europe may have been majority blue-eyed. Today, roughly 8 to 10% of the world's population has blue eyes, with concentrations reaching 80 to 90% in some Scandinavian regions. That's not random drift. That's not statistical noise. Something was selecting for this trait. Something was giving blue-eyed individuals an advantage that had nothing to do with survival in the traditional sense. The first theory, and probably still the most popular among researchers, is sexual selection. The idea is deceptively simple. Blue eyes were new. They were striking. They were different from anything anyone had seen before. And humans, it turns out, are absolutely fascinated by novelty, especially when it comes to choosing mates. Think about it from the perspective of a Neolithic farmer 8,000 years ago. You've spent your entire life in a village of maybe 50 or 100 people. Everyone you know has brown eyes, brown hair. Variations exist, sure, but within a narrow range. Then one day, someone shows up from a neighbouring settlement with eyes the colour of a clear winter sky. Eyes that seem to catch and reflect light in a way you've never seen before. eyes that are fundamentally, undeniably different. The attraction wouldn't be rational. It wouldn't be about survival or health assessment. It would be pure aesthetic fascination. The same impulse that makes humans collect rare shells, breed flowers for unusual colours, or pay fortunes for gemstones that serve no practical purpose. We are drawn to beauty. We are drawn to rarity. And in a world where everyone had brown eyes, blue eyes would have been impossibly rare, and therefore impossibly attractive. Sexual selection is powerful, insanely powerful. It's the force that gave peacocks their absurdly cumbersome tails, lions their dangerous manes, and male birds of paradise their elaborate courtship dances. These traits don't help survival. In many cases they actively hurt it. But they help reproduction, which is all evolution really cares about. If blue-eyed individuals were getting more mating opportunities simply because their eyes were considered attractive, the trait would spread rapidly through the population even if it offered zero survival benefits. There's even a mathematical model for this. It's called the Fisher's runaway selection. Once a preference for a particular trait gets established in a population, it can become self-reinforcing. Females prefer blue eyes. Males with blue eyes have more offspring. Those offspring inherit both the blue eye genes and the preference for blue eyes. The preference and the trait spiral upward together, driving each other to higher and higher frequencies. But there's a problem with the pure sexual selection theory. It requires the preference to emerge randomly, spontaneously, with no underlying reason. And that's possible, sure, but it feels incomplete. Some researchers think there must have been something else going on. Some environmental factor that gave the trait a subtle boost, creating the initial conditions where sexual selection could take over. Enter the vitamin D hypothesis. This theory suggests that blue eyes might have spread because they were part of a broader package of adaptations to low sunlight environments. Northern Europe during the Neolithic was dark, really dark. Long winters with weak sunlight, short summers with intense but brief solar exposure. And humans were struggling with a fundamental biochemical problem. They needed sunlight to produce vitamin D, but their bodies were designed for the bright, consistent sun of Africa and the Middle East. Vitamin D deficiency is serious. It causes rickets in children, weakening bones and causing deformities. It impairs immune function. It increases susceptibility to infections. In a population already dealing with the disease pressures of dense agricultural settlements, vitamin D deficiency could have been devastating. Natural selection would have favoured anything that helped people produce vitamin D more efficiently in low-light conditions. The solution, it seems, was to lighten up. Paler skin allows more UV radiation to penetrate, increasing vitamin D production. But here's where it gets interesting. The genes that control skin pigmentation also influence eye and hair colour. They're part of the same biochemical pathways. So as populations were selected for lighter skin to boost vitamin D production, they might have also, incidentally, been selected for lighter eyes and hair. Blue eyes, in this scenario, are just a side effect. A genetic hitchhiker piggybacking on the real adaptation, which was lighter skin. The trait didn't spread because it was useful. It spread because it was linked to something useful. And natural selection can't easily separate traits that are controlled by related genes. There's evidence for this. Populations with high frequencies of blue eyes also tend to have lighter skin and lighter hair. The traits cluster together geographically, all reaching their highest concentrations in Northern Europe where sunlight is weakest. And genetic studies show that many of the genes associated with eye colour are indeed related to the genes controlling skin pigmentation. But, and there's always a but, this theory has problems too. Some populations adapted to low sunlight environments without developing blue eyes. The Inuit, for instance, live at extreme northern latitudes but retained dark eyes and relatively dark skin. They solved the vitamin D problem differently, through dietary sources, eating vitamin D-rich fish and marine mammals. So blue eyes can't be a necessary adaptation to low sunlight. They're just one possible solution among many. Which brings us to the third major theory, and this one is controversial. It's called the rarity advantage in mate selection, and it suggests that blue eyes spread because they were rare, not because they were inherently attractive. The idea is based on observations from animal behavior and human psychology. When choosing mates, individuals often show a preference for rare variants within their population. It's a strategy for avoiding inbreeding and maintaining genetic diversity. In a population where almost everyone has brown eyes, a blue-eyed individual would be statistically likely to be less closely related to you than a random brown-eyed person. By preferring rare traits, you might unconsciously be selecting for genetic diversity in your offspring, which could provide subtle health advantages. As blue eyes become more common, the advantage would diminish, but by that point, other factors like social prestige or established beauty standards might maintain the preference. Some researchers think this mechanism could explain the initial spread of blue eyes, especially in small isolated populations where inbreeding was a real concern. The trait offered a visible marker of genetic novelty, making carriers attractive as mates, but the theory is speculative, hard to prove, and it doesn't explain why blue eyes specifically became the preferred rare trait rather than some other unusual feature. Then there's the theory nobody likes to talk about because it's boring, but might actually be the most important factor: genetic drift. Remember, Neolithic Europe wasn't one big homogeneous population. It was thousands of small villages, semi-isolated communities connected by occasional trade and migration, but largely breeding within themselves. Groups of maybe 100 to 500 people, sometimes smaller. In populations that small, random chance plays an enormous role in which genes spread and which disappear. If the original blue-eyed individual happened to live in a successful community, one that grew rapidly and sent out migrants to found new settlements, the trait could spread just because those migrants carried it with them. No sexual selection required, no survival advantage needed, just the random accident of being in the right place at the right time. Population bottlenecks would have accelerated this process. Disease outbreaks, famines, wars, any event that temporarily reduced population size would amplify the effect of random chance. If blue-eyed individuals happen to survive these bottlenecks in higher proportions, not because their eyes helped, but just by luck, the trait frequency would jump dramatically in a single generation. There's actually a name for this. It's called the founder effect. A small group splits off to establish a new settlement. By chance, that group happens to include a higher proportion of blue-eyed individuals than the parent population. The new settlement grows, and suddenly you have a community where blue eyes are common, not because they were selected for, but because of the random composition of the founding group. This could have happened repeatedly across Europe as agricultural populations expanded into new territories. Each new settlement founded by a small group carrying whatever random assortment of genes their founders happened to have. Some would have high frequencies of blue eyes, others wouldn't. Over time, the high-frequency populations might have been more successful for completely unrelated reasons. Maybe they found better land or avoided a plague, and their genes, including blue eyes, would spread further. The truth, almost certainly, is that all of these factors played a role. Sexual selection probably amplified a trait that genetic drift and founder effects had made somewhat common in certain populations. The vitamin D connection might have provided a subtle boost in northern latitudes, not enough to drive selection on its own, but enough to prevent the trait from being disadvantageous. Rarity advantage might have kicked in at certain times and places, adding another layer of selection pressure. Evolution isn't clean. It's not one mechanism working in isolation. It's a messy combination of multiple forces pushing and pulling genes in different directions, with random chance throwing in wild cards when you least expect it. What we know for certain is this: blue eyes spread faster than neutral drift alone would predict. Something was selecting for them, or at least not selecting against them, whether that something was human aesthetic preferences, biochemical adaptations to sunlight, random population dynamics, or some combination we haven't even considered yet, remains an open question. The debate continues. New genetic studies keep refining our understanding. Ancient DNA from Neolithic skeletons is revealing the timeline of blue eye spread with increasing precision, but the fundamental mystery remains. Why did one random mutation in one person 10,000 years ago end up reshaping the appearance of hundreds of millions of their descendants? Maybe there's no simple answer. Maybe the spread of blue eyes is less a story of evolutionary logic and more a story of historical accident amplified by human nature, a reminder that evolution isn't always about optimization and survival. Sometimes it's just about what happens to catch on, for reasons that are part biology, part culture, and part pure random chance. But whatever the reason, the result was undeniable. By the time written history began, blue eyes had become one of the defining features of European populations, a visible marker of ancestry and identity that would shape human culture in ways nobody could have predicted. For thousands of years after the mutation appeared, blue eyes remained rare, a curiosity scattered among the hunter-gatherer populations around the Black Sea. Maybe one person in 100 carried the trait, maybe fewer. These people were still living much like their ancestors had for tens of thousands of years. Small mobile bands following animal herds, harvesting wild plants, moving with the seasons. Population density was incredibly low, perhaps one person per square mile across most of Europe, sometimes less. Under these conditions, even if blue eyes provided some advantage, the trait would spread slowly, person by person, generation by generation. But then everything changed. Around 10,000 years ago, something happened in the Middle East that would transform human civilization forever. People figured out how to farm. Now, agriculture didn't appear suddenly. It emerged gradually over thousands of years as people in the Fertile Crescent, that arc of relatively fertile land stretching from Egypt through the Levant and into Mesopotamia, began experimenting with wild plants. They noticed that seeds dropped near their campsites would sprout the following year. They started deliberately planting them. They began selecting the most productive plants, saving their seeds, replanting them season after season. Without realizing it, they were practicing artificial selection, domesticating wild grasses into wheat and barley. The same thing happened with animals. Wild sheep and goats that tolerated human presence were easier to hunt. Eventually some groups stopped hunting them altogether and started keeping them penned near settlements. The tamest animals survived to breed. Within a few thousand years they had created domestic livestock, animals dependent on humans, but also animals that provided reliable meat, milk and materials without the uncertainty of hunting. This shift from hunting and gathering to farming and herding, what archaeologists call the Neolithic Revolution, changed everything about human life. Most importantly, it changed population dynamics completely. Hunter-gatherers need vast territories. A band of 25 people might require 100 square miles of land to sustainably harvest enough wild resources year after round. You can't pack hunter-gatherers densely. There aren't enough wild animals and plants to support them. But farmers can produce food from much smaller areas. 1 square mile of farmland could feed 50, 100, maybe even 200 people, depending on the crops and technology. Population density exploded. Within a few thousand years, farming communities in the Fertile Crescent went from tiny settlements of a few dozen people to villages of hundreds, then towns of thousands. And here's the thing about population growth. Rare genetic traits that might take tens of thousands of years to spread through small, scattered hunter-gatherer populations can spread much faster through large, dense farming populations. More people means more births. More births means more chances for genes to replicate, more chances for advantageous traits to multiply. But the real transformation happened when farming began spreading beyond its origin point. Around 8,000 years ago, farming communities from Anatolia, modern-day Turkey, began migrating into Europe. They brought their domesticated crops, wheat, barley, lentils, peas. They brought their domestic animals, sheep, goats, cattle, pigs. And they brought their genes, including genes from populations that may have already been mixing with the blue-eyed hunter-gatherers around the Black Sea. The archaeological evidence for this expansion is striking. You can trace it through pottery styles, house designs, burial practices. Starting around 6,500 BCE, distinctive farming cultures appear in Greece. By 6,000 BCE, they've reached the Balkans. By 5,500 BCE, they're spreading along the Danube River into Central Europe. By 5,000 BCE, they've reached France and the British Isles. This wasn't an invasion exactly. It was more like a slow wave of migration, farming families moving into new territories, establishing settlements, clearing forests for fields. Sometimes they displaced the existing hunter-gatherer populations, sometimes they coexisted, and sometimes they interbred. Ancient DNA from European archaeological sites tells us exactly what happened. The story is written in bones buried 5,000, 6,000, 7,000 years ago. Early European farmers who arrived from Anatolia had relatively low frequencies of the blue eye mutation. Most had brown eyes, but as they spread across Europe, they encountered hunter-gatherer populations who carried the trait at higher frequencies, especially in northern and eastern regions. When these groups met, they didn't just compete, they mixed. Farming men took hunter-gatherer wives. Hunter-gatherer men joined farming communities. Children carried genes from both populations, and with each generation of mixing, the blue-eye allele spread further into the farming populations that were rapidly growing and expanding across the continent. Within a few thousand years, something remarkable happened. That rare mutation that had been slowly drifting through small hunter-gatherer bands suddenly found itself in massive farming populations that were doubling every few generations. And if blue eyes really did provide advantages, vitamin D production, mate selection, reduced susceptibility to certain diseases, those advantages would be amplified in these new conditions. Agricultural societies created new selection pressures too. Living in permanent settlements with domestic animals exposed people to new diseases. Evolutionary biologists call these crowd diseases infections that only become sustainable when population density reaches critical levels. Measles, smallpox, tuberculosis, these plagues of civilization couldn't exist among scattered hunter-gatherers. Not enough hosts, but in farming villages with hundreds of people living in close quarters with their livestock. These diseases thrived. Any genetic variant that provided even slight disease resistance would be heavily selected for. We don't know if the genes linked to blue eyes provided such resistance, but we know the agricultural transition created intense new selection pressures across the genome. Lactase persistence, the ability to digest milk into adulthood, spread rapidly through European farming populations during the same period. Blue eyes might have been riding similar selective waves. The genetic evidence shows something else remarkable. As farming spread across Europe, it followed multiple paths. One wave moved through the Mediterranean, along coastlines, establishing farming communities in Italy, southern France, and Iberia. Another wave moved through Central Europe, following major rivers, the Danube, the Rhine, spreading agriculture through the heart of the continent. A third wave spread along the northern coast, reaching Scandinavia. Each wave encountered different hunter-gatherer populations with different genetic backgrounds. But remarkably, The blue eye trait increased in frequency along most of these paths. By 4,000 years ago, ancient remains from across northern and central Europe show blue eyes becoming common. Not universal, but no longer rare. Archaeological sites from Bronze Age Europe reveal something fascinating. Mass graves from ancient battles show mixed populations, warriors with different genetic ancestries fighting alongside each other. Burial goods show cultural exchange, tools and ornaments from distant regions. And physical remains show increasing frequencies of the blue eye variant spreading through these mixing, trading, warring populations. This wasn't a peaceful process. The spread of agriculture involved violence, displacement, population replacement. Genetic studies of modern Europeans show that the hunter-gatherer populations who originally inhabited the continent contributed relatively little to the ancestry of later populations. In most regions, they were largely replaced, but not completely. Their genes persist, mixed into the populations that came after, and one of the most successful pieces of hunter-gatherer heritage was the mutation for blue eyes. By the time the Roman Empire rose, blue eyes were already common in northern Europe. Roman writers noted the trait with interest when encountering Germanic and Celtic populations. Tacitus described the Germans as having blue eyes and reddish hair. These weren't their ancestors' eyes. These were eyes that had spread from a single mutant child through thousands of years of migration, mixing, and population growth. The success of the blue eye allele during the Neolithic and Bronze Ages represents one of the fastest known spreads of a visible genetic trait in human history. From rare mutation to common trait in perhaps 6,000 years. That's nothing in evolutionary terms, blink of an eye. What drove this rapid spread? Was it purely genetic drift, random chance amplified by population growth? Was it sexual selection, preference for the novelty of blue eyes driving mate choice? Was it linked selection, beneficial genes nearby on the chromosome being selected for and bringing the eye colour gene along for the ride? Or was it some combination, different factors mattering more in different times and places? We may never know for certain. What we know is that the Neolithic Revolution created the perfect conditions for a rare genetic variant to become common. Dense populations, rapid growth, extensive mixing between groups. And blue eyes rode that wave from the shores of the Black Sea to the Atlantic coast, from the Mediterranean to the Arctic Circle. By the time history began being written down, the transformation was complete. Northern Europe had become the land of blue eyes, a single mutation. One change in one gene in one child, perhaps 10,000 years ago, had spread to tens of millions of people. It had become part of the identity of entire populations, woven into mythology, culture, and eventually scientific curiosity. But the geography of this spread created a pattern that persists today. Blue eyes aren't evenly distributed across humanity. They cluster, and understanding why requires looking at the environmental conditions of Northern Europe and how they shaped the final chapter of this genetic story. Close your eyes for a moment and imagine a world map glowing softly in the dark. The continents are outlines of faint light, the oceans a deep, calm black. Now, one region starts to brighten. Not Africa, where our story began. Not the Middle East, not India, not China. It's the top of Europe. A thin horizontal band stretching from Iceland across the North Sea, through Scandinavia, over the Baltic states, and into the cold forests of Russia. That's where the blue is. If you could see eye colours from orbit, Northern Europe would look like someone spilled ice into the human gene pool. Let's start with a number that almost doesn't feel real. Estonia, a small country on the Baltic Sea. Forests, lakes, long winters, short summers, and an eye colour profile that looks like a glitch in the simulation. Genetic surveys suggest that around 89% of ethnic Estonians have blue eyes. Not lightish, not sometimes hazel in summer sunlight. Blue. stand in the middle of Tallinn's old town on a winter morning, and almost 9 out of 10 faces passing you on the street are carrying the same rare mutation that began with a single child, somewhere, sometime, thousands of years ago. That's not normal. That's not random. Something happened here, and Estonia isn't alone. Across the Baltic Sea, in Finland, Sweden, Norway, Denmark, and down through Latvia and Lithuania, blue eyes are common enough to be the default. In some of these populations, more than half the people you meet will have light eyes, blue, grey, green, or mixtures. This creates a striking pattern that geneticists and anthropologists call a cline, a gradient, a slow, steady shift, not from mountain to valley, but from north to south. In Northern Europe, blue and other light eyes can reach 70, 80, even close to 90% in some communities. Move south inch by inch, and the blue begins to fade. Through Germany and Poland, the percentage drops. Through France, Austria, the Czech lands. Finally into Italy, Greece, Spain, and the Balkans, where brown eyes dominate again, and blue becomes a minority colour, a curiosity rather than a norm. It's not a sharp border. There is no line on the map where blue stops and brown begins. It's more like the way dusk turns into night. A slow deepening of pigment as you move closer to the equator. What drives this gradient? Part of the answer is light. Not light in the poetic sense, but literal sunlight. Near the equator, solar radiation is intense. For early humans with dark skin and dark eyes, that wasn't just a cosmetic detail. It was protection. Brown eyes have more melanin, the same pigment that darkens skin. Melanin doesn't just colour the iris. It absorbs and scatters light, including ultraviolet radiation. That reduces glare, protects the inner structures of the eye, and shields delicate tissues from damage. In Northern Europe, especially in winter, the sunlight that reaches the ground is weaker. Days are short. The sun rides low in the sky. For much of the year, the world is cold and dim. In these conditions, having slightly less pigment in your iris may not have been a major disadvantage. For some individuals, it might even have been very mildly beneficial, allowing a bit more light into the eye, improving vision in low-light conditions, or perhaps simply not costly enough for natural selection to care. So as humans moved north into darker, colder lands, the intense pressure to maintain brown, heavily pigmented eyes relaxed. And when selection relaxes, strange things can happen. A single mutation, somewhere in the gene region that controls eye colour, can drift through the population almost unnoticed. Not because it is helping, but because it isn't being strongly punished. Over time, in the right conditions, it can go from rare to common, and from common to dominant. But that still doesn't explain why Northern Europe specifically became the great reservoir of blue. After all, there are many dark, cold places on Earth. The northern parts of Asia, the high plateaus of Tibet, the mountains of the Americas. None of them developed anything like Estonia's 89% blue-eyed majority. To understand why, we have to think not just about latitude, but about people. How many there were, where they lived, and who they were allowed to have children with. Northern Europe, for most of history, was a patchwork of small, relatively isolated populations. Think fjord valleys separated by mountains and water, island communities ringed by freezing seas, villages surrounded by dense forests, where travelling to the next settlement might mean walking for days. These weren't fully cut off from each other. Trade, migration, and intermarriage still happened, but they were separated enough, long enough, for something powerful to take hold. The founder effect. Imagine a small group leaving a larger population. Maybe they cross a narrow strait into a new land. Maybe they move into a valley that no one else is using. By chance, this little offshoot group carries a higher frequency of some rare trait than the population they left behind. not because it was chosen, just because that's who happened to go. If one of those founders had blue eyes, or carried the mutation that produces blue eyes, then their descendants will, on average, have more blue-eyed children than the original group. And if that new community remains relatively small and somewhat isolated, the trait can spread rapidly within it. Over generations, you can get whole villages, whole regions, where the weird trait from the founding group becomes the norm. This is how rare alleles can explode in frequency in small, semi-isolated populations. Not through grand adaptive battles, but through random luck, geography, and the slow arithmetic of family trees. Northern Europe, with its post-Ice Age landscapes of lakes, islands, and peninsulas, was perfect for this. Small farming communities hugging coastlines, fishing villages at the ends of long, narrow inlets, farming hamlets and clearings far apart, where people mostly married people they could actually reach on foot. Add in another factor: repeated bottlenecks and migrations. The last ice age reshaped Europe again and again, pushing people south into refuge, then allowing them to spread back north as the glaciers retreated. Each wave of recolonization could have magnified certain traits in some regions and erased them in others. In some of those recolonizing groups, blue eyes were common. In others, they were rare. In Northern and Eastern Europe, those blue-heavy groups seem to have left a particularly deep mark. Now contrast that with the Mediterranean. Southern Europe has its own history of small villages and mountain valleys. But it also has something else: millions of years of sunlight and thousands of years of dense, interconnected human civilization. The Mediterranean basin became a highway. Phoenician sailors, Greek colonists, Roman legions, Arab traders, Ottoman armies, cities like Rome, Athens, Carthage, Alexandria, ports where people from Africa, Europe, and Asia met, traded, lived, and had children together. All of that mixing kept brown eyes common. Darker pigmentation remained useful under stronger sun. The massive population sizes and continuous gene flow made it harder for rare, neutral traits like blue eyes to rise to dominance through simple drift or founder effects. So while blue eyes do appear in Italy, Spain, Greece, and the Balkans, they tend to be more scattered, more diluted in a sea of brown. A recessive note rather than the main theme. Yet the story doesn't stop in Europe, because blue eyes did not stay where they began. Today you can find blue-eyed faces in places where the original mutation almost certainly never arose, in parts of the Middle East, Central Asia, and North India, where past migrations and ancient contacts left their genetic fingerprints. In Afghanistan, where some ethnic groups show surprisingly high rates of light eyes. Among certain communities in the Levant, where centuries of crusaders, traders, and mercenaries left descendants. And, of course, across the Americas, Australia, South Africa, and beyond, the result of European colonization and migration over the last 500 years, people carrying that old northern mutation, boarding ships and trains and planes and scattering blue eyes across the planet. There are even small, almost mysterious pockets. Remote villages where light eyes show up more often than you'd expect given the surrounding populations. Sometimes this can be traced to a known historical event, a shipwreck, a military outpost, a trading colony that left a handful of mixed descendants. Sometimes the history is more obscure, half remembered in local legends about foreigners who came long ago. Wherever they appear, these pockets tell the same quiet story, that once a mutation exists, once it survives that first fragile generation, it can ride on human journeys far beyond the environment that first allowed it to spread. So when we say blue eyes are European, we're really saying something more specific. They are Northern European in origin. They became common in a band of cold lands bordering the Baltic and the North Sea, where low light, repeated bottlenecks, founder effects, and small, semi-isolated farming and fishing communities let a strange, unnecessary trait spread almost unchecked. Yet those same blue eyes no longer belong to one region, any more than language or tools do. They're a local mistake with global distribution, a quirk of geography and history that now looks back at you from faces on every continent. And behind every one of those eyes is the same question. If this trait wasn't needed, why did it last? Why did some communities embrace it, even prefer it? Why did a mutation that did almost nothing go from a single child's iris to millions of people staring into mirrors, wondering how something so fragile became so common? To answer that, we have to leave the map behind and look not just at where blue eyes are, but what we decided they meant. Blue eyes didn't just exist in the past, they meant something. Once the mutation had spread through parts of Europe, it didn't just sit quietly in people's skulls. Other humans noticed. They watched those pale irises in firelight, in battle, in trade negotiations across primitive harbours, and slowly, over thousands of years, they started to wrap stories, fears, and fantasies around them. Because when something is rare, humans don't leave it alone. We give it meaning. In the far north, where winter nights could swallow half the year, blue eyes became entangled with the sky itself. Norse poets described gods with eyes like ice and storm. Odin, the one-eyed wanderer, was often imagined with a piercing, pale gaze, an eye that could see beyond the human world. The sagas don't give us a tidy colour chart, but later Scandinavian folklore is full of blue-eyed trolls, blue-eyed maidens, blue-eyed spirits of snow and sea. When your world is built of grey rock, white snow, and blue horizon, the colour of your eyes naturally borrows from the landscape. Further south in ancient Greece, the imagination took a different route. Greek writers used the word glaukos for eyes, a term that could mean light, grey, blue, or green, shimmering like the sea on a windy day. Athena, goddess of wisdom and war, was glaukopis, often translated as bright-eyed or grey-eyed Athena. Some scholars think this might reflect a memory of lighter-eyed peoples to the north, transformed into divine traits. The Greeks knew that not everyone's eyes looked like theirs. They wrote about the Thracians, the Scythians, the people beyond the familiar world, often describing them as tall, fair-haired, light-eyed. Strange, impressive, a little unsettling. The Mediterranean world was ringed by these encounters. As Phoenician traders sailed the coasts, as Greek colonists moved into the Black Sea, as Roman legions pushed into Gaul, Britain, and Germania, they kept finding people whose eyes didn't match their own. Brown-eyed scribes recorded blue-eyed warriors. Dark-haired city-dwellers stared across wooden tables at pale-eyed chieftains. Herodotus, the Greek historian, describes the Badini, a northern people he calls blue-eyed and ruddy. Roman authors like Tacitus talk about the Germans with their fierce blue eyes and reddish hair, almost as if they were a different category of human. Wilder, more dangerous, less civilized but more physically imposing. For Mediterranean empires, blue eyes became a shorthand for the barbarian north, the people beyond the walnuts and olives, beyond the vineyards and marble temples out in the forests and mist. To the Romans, those pale eyes were unsettling in battle. Imagine a line of soldiers used to warm brown eyes across the forum, suddenly facing a wall of men whose irises seemed almost colourless in the cold light, pupils tiny pinpricks against grey or icy blue. It's not surprising that writers began to associate that look with ferocity, stubbornness, and a kind of raw, untamed strength. But even in those early stories, you can already see something important happening. Eye colour, which began as a random mutation in one child, was drifting into the realm of symbols. Light eyes were becoming a sign of them rather than us. Over centuries, that symbolic freight only got heavier. In medieval Europe, blue eyes acquired their own layers of meaning. Christian art painted under northern skies by northern artists often gave the Virgin Mary soft blue eyes, matching the blue of her mantle. Heaven, in these paintings, was a blue dome overhead. The saints stared out with pale irises, luminous against golden halos. It wasn't universal. Plenty of paintings showed dark-eyed holy figures, but there was a trend. Holiness, purity, and softness began to wear a pale gaze. At the same time, blue eyes also carried the legacy of the northern warrior. In epic poems and romances, fair-haired, light-eyed knights and queens appear again and again, not because everyone actually looked like that, but because that combination had become a literary shorthand. Noble, high-born, chosen by fate. Brown eyes might just be eyes, but blue eyes got mentioned, highlighted, made special. Writers noticed in real life too. Alexander the Great was often described as having heterochromia, one dark eye, one light, and ancient authors treated this as a sign of his uniqueness, his destiny. Centuries later, tales about charismatic leaders and conquerors would linger on the colour of their eyes. The steely blue gaze of a general, the cold blue stare of a ruler. Whether those descriptions were literally accurate mattered less than what they communicated. Power, distance, otherness. It wasn't always positive. In folk stories across Europe, blue eyes could belong to witches as easily as to saints. A gaze that seemed to see through you became eerie, uncanny. Eyes that didn't match the majority sometimes triggered suspicion. The same mutation that could be praised in a princess could be feared in an old woman living alone at the edge of a village. Art kept amplifying these associations. As painting techniques advanced, artists learned how to make eyes glow, catch light, hint at inner life. In Renaissance portraits from Northern Europe, pale irises stand out dramatically against dark backgrounds and rich fabrics. The effect is almost hypnotic. Look closely at portraits by Dürer or Holbein, and you'll find sitters whose blue or grey eyes seem to follow you across the room. These weren't random details. Patrons wanted to be recorded as striking, intelligent, present. A vivid eye colour helped. Literature followed suit. By the 19th century, European novels and poems were filled with blue-eyed heroines described as innocent, ethereal, or fragile. Poets compared their lovers' eyes to the sky, to forget-me-nots, to the sea. Children's stories and fairy tales leaned into the trope. Pale eyes as a sign of inner goodness, of royal birth, of being chosen. Not always, but often enough that the pattern became hard to ignore. But as the modern age approached, the story took a darker turn. The same human tendency to attach meaning to differences that once produced myths and paintings began to harden into something much more dangerous, pseudoscience. In the 19th and early 20th centuries, some European thinkers tried to classify humans into rigid races based on physical traits, skull shape, hair type, skin tone, and yes, eye colour. Blue eyes were placed on charts, measured, recorded, ranked. What had once been a neutral variation, a side effect of melanin distribution in the iris, was reimagined as evidence of superiority or inferiority, depending on the ideology. In some racial theories, especially in Northern Europe, blue eyes were elevated as markers of a supposed pure or noble lineage. These claims weren't based on real biology. They were stories, dressed up in the language of science, used to justify power and hierarchy. During the rise of fascism in the 20th century, those ideas became state doctrine in some countries. Posters, schoolbooks, and propaganda films idealized children with blonde hair and blue eyes as the future of the nation. People whose eyes and faces didn't fit the image, including millions of perfectly ordinary Europeans with brown eyes, were subtly or openly coded as lesser. The same mutation that had once been mysterious now became a weapon, part of a deadly system of exclusion, persecution, and genocide. There is no genetic basis for those hierarchies. Eye colour doesn't map cleanly onto intelligence, morality, or worth. But myths can be powerful, even when they're false. For a time, blue eyes were dragged into one of the darkest chapters of human history, used as a visual shortcut for belonging or not belonging, safety or danger. Even after the fall of those regimes, the echoes remained. Advertising in the 20th century often leaned into a similar aesthetic. Pale eyes as the default for beauty in many Western markets, even when the audience didn't share that trait. Film and television frequently cast blue-eyed actors as heroes, brown-eyed characters as ethnic, foreign or other. The mutation that started with one child in prehistoric Europe was still shaping how humans categorized each other, unconsciously or deliberately. And yet, blue eyes have never had a single meaning. Around the world today, they can be seen as exotic or ordinary or striking or unremarkable, depending on where you live. In some cultures, they're still associated with foreignness. In others, they're so common that they barely register. Artists continue to paint them. Photographers continue to highlight them. Writers still mention them when they want a character to stand out. If you trace all those stories back, the Norse gods, the Greek epithets, the Roman soldiers unnerved by northern warriors, the medieval saints, the romantic heroines, the racist propaganda, the modern movie posters, they all point to the same biological accident. A pigment change in the iris, less melanin than average, light scattering differently in the front of the eye, a tiny genetic change that had no built-in meaning at all, until other humans started looking at it and decided, for better and for worse, to give it one. The story you might have heard in school goes like this. Brown eyes are dominant, blue eyes are recessive. Two brown-eyed parents can sometimes have a blue-eyed child, but two blue-eyed parents will never have a brown-eyed one. End of story. Simple, neat, satisfying, and also almost entirely wrong. It isn't that this story is a total fiction. It's more like a children's version of a much stranger book, a map of a continent that only draws two cities and ignores everything else. For most of the 20th century, that little map was all we had. A single eye-colour gene, a tidy Punnett square, a sense that the universe liked clean rules. Modern genetics has taken that map, turned it over, and quietly drawn an entire world on the back. When scientists began sequencing human genomes in large numbers, they started looking for the gene that caused blue eyes, or brown eyes, or green eyes. What they found instead was a genetic chorus. Dozens of regions scattered across the genome, subtly shifting how much pigment gets made, where it's stored, how it's packed, how light bounces back out of the iris. The old textbook model did have one thing roughly right. A region near a gene called OCA2 on chromosome 15 really does explain a lot of the difference between very dark brown eyes and light blue ones. A neighbouring control switch called HERC2 sits like a dimmer on a wall. Turn the dimmer up, and OCA2 helps pump out more pigment. Turn it down, and the iris becomes paler, lighter, more translucent, letting the blue of scattered light shine through. But that's only the beginning. Other genes step in like quiet background actors, each changing the scene a little. Some tweak how much melanin is made. Others adjust how it's packaged into tiny granules in the iris. Some influence the thickness of the iris tissue itself, which changes how light scatters. Add them all together, and you don't get a simple on-off switch. You get a spectrum, a gradient. The soft slide from nearly black to dark chocolate brown, to amber, to hazel, to green, to grey, to icy blue. This is why the old brown is dominant, blue is recessive rule keeps failing in real life. Two brown-eyed parents can have a green-eyed child or a blue-eyed one, not because the laws of genetics have been broken, but because so many different genes are interacting at once. It's like trying to predict the exact shade of a sunset by knowing only the position of the sun. You need the humidity, the dust in the air, the angle of the clouds. All the details matter. If you could line up every human on Earth by eye colour, from darkest to lightest, it wouldn't look like a few neat bins. It would look like a continuous river of colour. Each pair of irises carrying the history of dozens of tiny genetic decisions, made quietly over thousands of generations. In that river, some eyes refuse to fit into the usual categories at all. Think of heterochromia, one eye blue, the other brown, or an iris that looks split, half one colour, half another. Sometimes this happens because of a mutation that occurred after conception, so that some cells in the iris carry slightly different instructions than others. Sometimes it's linked to developmental quirks, or rarely to medical conditions. But often it's simply another expression of how finely tuned, how locally varied eye pigmentation can be. The iris isn't a flat, uniform surface. It's a landscape. Hills, valleys, folds, layers, tiny variations in blood supply, in pigment cell density, in connective tissue. Change that landscape in one small region, and the way it scatters and absorbs light will shift. A ring of copper around a blue centre, a burst of gold in a field of green, a dark fleck like a tiny planet frozen in orbit. To the person wearing those eyes, it may just be a quirk. To genetics, it's a reminder. Even within a single iris, colour is not one thing. It's a mosaic. There are other illusions at play too. Many people say their eyes change colour with the weather, or with what they're wearing, or with their mood. On a bright day, their eyes look turquoise. On a cloudy one, grey. In one photograph, their eyes seem almost green. In another, clearly blue. The iris isn't actually manufacturing new pigment when you put on a different shirt. Instead, your eyes are working like very subtle mirrors. The front of the iris is composed of layers that scatter light, a bit like the sky does. Blue light has a shorter wavelength, so it scatters more. Reds and browns sink deeper. Clothing, surrounding colours, the warmth or coolness of the light, all change which wavelengths are most prominent. Wear a deep green shirt under warm indoor light, and the flecks of yellow in your iris might stand out, making your eyes seem greener. Step into cool bluish daylight in a grey hoodie, and those same eyes might fade toward blue or slate. Your eyes are not changing, but the light that reaches them, and the light that bounces back to the observer, is constantly shifting. Then there are colours that were long treated as awkward exceptions in the schoolroom story. Green eyes, hazel eyes, eyes that don't fit neatly into the categories on a lab worksheet. Green eyes, especially common in parts of Europe and West Asia, are not made by some special green pigment. They are the result of intermediate amounts of melanin plus the way the iris scatters light. There's enough brown pigment to warm the colour, but not enough to dominate. Blue scattering adds itself on top, and our brains read the mixture as green. In some people, a hint of yellowish lipochrome pigment in the iris intensifies this effect, creating eyes that look like seawater over a sandy bottom. Hazel eyes are another blend. Often they're eyes with a brown or amber base, overlaid by regions of lower pigment density. The result is a shifting mixture of golden brown, green, and sometimes grey, depending on light and surroundings. Hazel eyes are like the midway point on a long gradient, where multiple pigment levels and scattering patterns overlap. When you begin to see eye colour as a spectrum of melanin amounts, arranged in different layers, modulated by structural scattering, the mystery of green and hazel eyes dissolves into something more interesting. They're not exceptions, they're inevitable. Even the idea of eye colour as something fixed, decided once in early childhood, and then unchanging, turns out to be less certain than it sounds. Most babies of European ancestry are born with blue or greyish eyes. Over the first few years of life, melanin-producing cells in the iris wake up, influenced by genetic programs and indirectly by hormones. For many children, eyes darken with age, drifting from blue to hazel, from hazel to brown. In other parts of the world, newborn eyes may already be dark, but they can still shift in shade and richness as pigment accumulates. The changes don't always stop with childhood. Hormonal shifts in adolescence, pregnancy, or even later life can subtly alter eye colour. In some people, certain medications, especially ones that affect melanin production, may cause gradual darkening, particularly around the pupil. Diseases that damage the iris or its pigment cells can produce localized lightening or darkening. These shifts are usually small, sometimes only noticeable in old photographs, but they remind us that even eye color is not perfectly still. It's a state, not a commandment. With all this complexity, you might wonder what modern genetics can actually tell us about predicting a child's eye color. The answer is, more than before, but far less than the old Punnett square promised. Today, geneticists can look at a handful of key variants, especially in OCA2, HERC2, and a few other pigmentation genes, and make reasonably accurate predictions for broad categories, likely dark, likely light, somewhere in between. For people of European ancestry, some DNA tests can say with high confidence whether a person is more likely to have very light blue eyes versus deep brown ones. But once you start asking finer questions, exact shade, amount of green, presence of hazel tones, the confidence drops. That's because eye color is a textbook case of what scientists call a polygenic trait. Many genes, each contributing a little, plus environmental factors and random developmental variation. In such traits, prediction is a matter of probabilities, not certainties. Two brown-eyed parents with a mixture of light and dark variants hidden in their DNA can absolutely have a blue-eyed child. Two blue-eyed parents will almost always have blue-eyed children, but even almost always leaves a sliver of possibility, especially in populations with diverse ancestry. The genome remembers more than the eyes reveal. In the end, the science of eye color turns out to be a story perfectly in tune with human history itself. What once looked simple and orderly, from a distance in the dim light of early knowledge, unfolds into intricate networks, overlapping causes, branching paths that lead to unexpected outcomes. The blue of a northern iris, the green of a coastal village, the deep brown of ancient equatorial lineages, none of them are single decisions written into a single gene. They are emergent properties of a system tuned by millennia of migration, survival, and chance. A living map traced not with ink on paper, but with light passing through the eyes of every person who has ever opened them to the world. Picture a news headline drifting across your phone screen sometime in the last few years. Scientists say blue eyes will be extinct in 200 years, or maybe it was 150 or 500. The numbers change, but the story is always the same, a sense of urgency, a vanishing treasure. Get your look at blue eyes now, before they disappear forever. It sounds dramatic. It sounds like a warning. It's also almost certainly wrong, because evolution doesn't work on headlines. It works on math. Blue eyes are caused, mostly, by a recessive variant near a gene called OCA2. Recessive just means this: you need two copies of the blue eye version to show it. If you have one blue version and one brown version, your eyes will probably look brown or hazel. The brown masks the blue. But the blue is still there, quietly folded into your DNA, waiting. And this is where the supposed extinction story falls apart. For a trait controlled by a recessive variant, disappearing from sight is not the same thing as disappearing from the gene pool. You can bury a recessive allele under layers of dominant ones, and it will just keep moving through generations, invisible but intact. Unless something is actively removing it, killing its carriers before they reproduce, or making them dramatically less likely to have children, the gene can linger for an astonishingly long time. Think back to the bottleneck your ancestors once survived. A world with fewer than 2,000 breeding humans. Yet here you are, carrying their chromosome fusion, their ancient immune system variants, their memories written in your cells. Those genes made it through 117,000 years of near extinction. A blue-eye allele surviving a few centuries of global mixing? That's easy mode by comparison. So what's really happening? Over the last few hundred years, humans have started doing something new in evolutionary terms, something our Paleolithic, Neolithic and even medieval ancestors barely did at all. We began moving, everywhere. 1,000 years ago, a person born in a fishing village on the Baltic coast might live their entire life within a few dozen miles of that shoreline. Their children would marry people whose ancestors had also lived by that same cold grey sea for as long as anyone could remember. The gene pool was small, local and predictable. Now imagine modern Europe, and then don't stop there. Imagine flights from Lagos to London, from Warsaw to Chicago, from Mumbai to Oslo. Imagine students in Erasmus programs, migrant workers, refugees, digital nomads who treat continents like neighborhoods. For most of human history, blue eyes were largely contained within certain populations, especially around the Baltic, Scandinavia, parts of northern and eastern Europe. High frequencies and smallish, somewhat isolated pools. Plenty of people had 2 copies of the blue variant, so the eyes showed. Global migration changed the game. Now those blue-eye alleles are mixing into much larger, more diverse populations. A person with blue eyes in Sweden has children with a partner from West Africa, or South India, or the Middle East. The kids might have brown or hazel eyes, because brown is dominant. But inside their genomes, one of those chromosomes is carrying that ancient blue-eye variant as faithfully as ever. Zoom out another generation. Those brown-eyed children grow up and have kids of their own, maybe with someone else who secretly carries a blue-eye allele, maybe from a completely different part of the world. 2 hidden copies meet again in the same child, and suddenly, blue eyes look out at the world once more. From the outside, it might look like blue eyes are disappearing, because they're visibly rarer in more mixed populations. But from the inside, from the perspective of the gene itself, it's just travelling, leaving the narrow river valley of northern Europe and streaming into a continental-scale ocean of humanity. Geneticists who model these changes don't predict extinction. They predict dilution and redistribution. In places like Scandinavia, Estonia, or parts of northern Germany, where blue eyes once dominated, the percentage of blue-eyed children will probably continue to decline over the next few centuries, simply because people are partnering across a wider range of ancestries. In a small, relatively closed village, the chance of 2 blue allele carriers meeting was very high. In a global city, it's still possible, but the probabilities spread out. At the same time, something else is happening. Those same models suggest that blue-eye alleles will become more widely scattered across the globe than ever before. Fewer towns where everyone is blue-eyed. More cities where almost everyone knows at least one person with blue eyes whose grandparents were born 1,000 miles apart, maybe on different continents. The total number of blue-eye alleles in the human species isn't being sucked into a black hole. It's being shuffled like cards in an ever larger deck, and unless there's strong selection against them, some real survival or fertility disadvantage, which current evidence doesn't support, they'll just keep circulating. Hidden in brown-eyed parents, visible in the occasional child, popping up in families where no one remembers having a blue-eyed ancestor at all, because the memory was lost long before the gene was. So when will the last blue eyes vanish from Earth? Probably never, in any meaningful human time frame. We're far more likely to see blue eyes become a rarer but more globally randomized trait than to see them truly go extinct. Even computer models that assume high levels of mixing and no particular advantage for blue eyes don't usually trend toward 0. They tend toward low, scattered frequencies. a faint but persistent echo of a very old mistake. There's another layer to this too. Technology. We already have the ability to predict eye colour from DNA with impressive accuracy. We're starting to edit genes in embryos in limited medical contexts. Cosmetic gene editing is still the stuff of sci-fi and speculation, tightly restricted by ethics and law, but it's no longer unthinkable. If a world ever arrives where parents choose traits like eye colour the way they choose paint for a nursery, blue eyes won't disappear. They'll be ordered. That future may never fully come to pass. Cultural values shift. Ethics harden and soften. But the mere possibility means this. If anything, the danger for blue eyes is not extinction. It's over-curation, turning a wild evolutionary accident into an aesthetic option on a clinic form. And that raises a different question. Does any of this actually matter? If 5,000 years from now there are only a handful of blue-eyed people on the planet, or if there are millions, will the universe notice? Will the Earth spin differently? Will the grand story of life be altered in any measurable way? On a cosmic scale, eye colour is trivial. It's a small tweak in melanin distribution inside a thin layer of tissue at the front of the eye. It doesn't change your consciousness. It doesn't determine your worth. It doesn't alter the deep, ancient fact that every human alive descended from the same scattered bands of survivors. But on a human scale, it does something peculiar. That tiny mutation, probably in a single child living somewhere near the Black Sea thousands of years ago, changed how people saw each other. It became a signal, a symbol, a source of myths and stories. It influenced beauty standards. It shaped art, poetry, propaganda, advertising, religion. It helped define who was seen as us and who was seen as other in ways both subtle and brutal. A pigment glitch in the iris reached forward through time and tangled itself in politics, romance, prejudice, identity. And now, in the age of planes and algorithms and DNA tests ordered on your phone, it continues to ripple. Two strangers meet on a flight from Toronto to Dubai. One has eyes the colour of wet sand, the other the pale grey of winter sky. Their children's eyes will carry some combination of alleles shaped by ancient farmers, steppe herders, hunter-gatherers who once watched glaciers creep across the horizon. Blue eyes are not going extinct. They're doing what human traits always do when borders melt and distances shrink. They're dissolving into the vast, swirling pattern of our shared genome. Maybe, as you fall asleep, that's the more interesting truth. Not whether blue eyes fade or endure, but how persistent this single accident has been. How far its influence has stretched. From a child who once opened their eyes under a Neolithic sky and startled their parents with that impossible colour, all the way to you, lying here in the dark, listening to a story about them. The mutation is old. The myths are newer. The genes will keep moving quietly long after the headlines stop. And somewhere, generations from now, a newborn will open their eyes for the first time. The room will go quiet. Someone will lean in, surprised. They're blue, they'll say, and an ancient mistake will have survived yet again. So now we've come full circle. From a world where almost every human eye was some shade of brown, to a single child, born somewhere around the Black Sea, carrying one tiny copying error in their DNA, to a planet where hundreds of millions of people wake up every morning and look out at the world through blue eyes that, strictly speaking, were never supposed to exist. A change in one gene, a small alteration in how pigment is produced and placed in the iris. No new organ, no new limb, no new superpower. Just a subtle shift in how light scatters as it passes through the front of the eye. And yet that small shift travelled through time. It rode from parent to child, across villages and tribes, through winters and famines and wars, across the ice of Europe and the fields of the Neolithic, sailing with traders, marching with armies, sitting quietly by hearth fires while stories were told in languages we no longer remember. For that mutation to reach you, every single ancestor in that chain had to survive long enough to have children. They had to avoid accidents and infections, pick the right moment to migrate or stay, find enough food in hard years, and choose partners who, without knowing it, carried the same fragile thread of DNA. When you trace it back, it feels less like inevitability and more like a long, improbable coin toss that just kept landing on its edge. We like to imagine human traits as deliberate, as if they were designed for a purpose, as if blue eyes appeared because the universe needed them, or because beauty was waiting to be invented. But what this story really shows is how much of us is built on accidents that didn't get erased. A cosmic ray here, a copying error there, a slightly different climate, a migration that almost didn't happen, a hunter who walked north instead of south one winter and met a different group of people on the other side of a frozen river. From those tiny divergences, whole futures unfold. Blue eyes are just one example we can see in the mirror. The same quiet chaos sits behind everything about us. The way some of us can digest milk as adults, the way some of us handle thin air in the mountains or resist certain diseases, the shape of your nose, the texture of your hair, the way your body stores fat in lean times. None of it was planned. Every trait you carry is the result of the same ancient game: mutation, survival, and time. Most mutations vanish without a trace, a few slip through. Fewer still find themselves in the right place at the right moment in history to spread. And sometimes, when the world shifts, when farming begins, when diets change, when sunlight weakens at higher latitudes, a trait that was once irrelevant suddenly matters. It might make you slightly healthier, slightly more attractive to would-be partners, slightly more likely to have children who live long enough to have children of their own. Generation after generation, those tiny slightlies add up. So when you see blue eyes in a crowded train station, or in the reflection on your phone screen, you're looking at the ghost of a long-ago accident that the world never quite managed to erase. And beyond that, you're looking at a reminder of something much larger. Every human face is a museum of ancient mistakes that worked well enough to stay. Every shade of eye and skin and hair is evidence that there was never one correct way to be human, only countless experiments in survival, some of which happen to make it this far. If you've enjoyed drifting through this story, from a single mutation in a Neolithic child to the blue eyes that light up photographs and paintings and streets today, you might gently tap the like button and leave a comment telling us where in the world you're listening from tonight. If you'd like to hear more journeys like this, more slow walks through deep time and quiet history, you can subscribe so you don't miss the next one. And if you ever feel like going one step further, there's an optional channel membership you can join to support these stories directly. It helps keep the lights on behind the scenes, but it's never expected and completely up to you. Your presence here, listening, is already more than enough. For now, you can let the ideas soften and blur, the migrations fade into mist. The farmers lay down their tools, the first blue-eyed child closes their eyes beside a hearth that has been cold for thousands of years. All that remains is a quiet awareness that you are part of this long, improbable chain, a living continuation of accidents, choices and survivals stretching back beyond memory. As you drift towards sleep, you can imagine all those ancestors behind you, layer upon layer of lives forgotten by history but written, softly, into every cell of your body. Their storms are over, their winters have passed, their strange, lucky mistakes have arrived here, in this calm moment, with you. Let your breathing slow, let your thoughts thin out, like clouds at dusk. And if your eyes close now, brown, blue, green, or something in between, know that somewhere, far back in time, A small random change once opened the door for you to be exactly as you are. Good night.